Hi, everyone. Welcome. We are today talking about the commutative property. So the commutative property works for multiplication and it works for addition. So we're going to talk about both. We're going to see some examples in action. And I hope this is really helpful for you because the commutative property is something that we use all the time, but we don't necessarily know what the word is or what it means. And I got to tell you for myself, and probably a lot of your other teachers, we didn't learn about this until we were in high school or maybe even college. Now, we used the principles of this all the time, but we didn't necessarily know what the words were or how to apply them with particular discretion. And that's what we're hoping that you can learn from today's video and also from your practice. So, commutative property. First of all, you've seen that I've underlined a part of the word commutative. Now, if you say it very clearly, you hear the two T's, commutative. But a lot of times people say it a little softer, commutative. Now, notice that the part of the word I underlined, commute. You may have heard your family talking about that word because you might hear it on the radio in the morning if you're in the car when you're coming to school. A lot of people talk about the morning commute on your way. Well, what does that mean? Well, what it means is that our family gets into our car oftentimes, but maybe not. Maybe we take the bus or maybe we walk, but somehow we get from our house to our work. And we do that every morning. So going from our house to our work, that's the morning commute. Now, a lot of times on the radio, they talk about it because people are in their cars listening to the radio. They might be riding the bus. They might have the radio on so they can hear some news and some music. So a lot of times you'll hear announcers on radios talking about the morning commute. It's also the time that we think of people getting caught in traffic jams. So if you're stuck in a traffic jam, you're listening to the radio because you got nothing else going on. So that's the morning commute. Now, that helps us remember commutative property because it has the same parts of the words in there. It means going from one to the other. Now, there's also an evening commute. Same thing, going the other way. Our families are done at work. They get in their car, they get on their bike, they walk, they ride the bus, they take the train, whatever it is they do, and they get back home. So that's going the other way. Now, if you've had me in class before, you may have heard me ask you this question. But if you haven't, or if you've forgotten, here's the question. Is the morning commute longer when you go from your house to work? Is that longer? Or is it longer when you leave your work and go back to your house? Now, don't get confused with time. It might take longer if you got caught in a traffic jam or for whatever reason you were delayed. That's okay. That's what we're talking about. We're just talking about the distance. Is it further to go from your house to work or from work to your house? Now, some kids would say, well, it depends on what route you take. Maybe you have to stop at the grocery store on the way, or maybe you have to pick someone up from school or something. Those are all important things. But what if it was exactly the same route? Start at your house, drive at exactly the same roads. Whether you're going faster or slower, doesn't matter because it's distance we're talking about. So go on exactly the same road to work. Then you come out of work. You don't stop anywhere else. Don't stop and get groceries or anything like that. You just drive from where you parked. You drive right back and park right in front of your house. Which one is more? Which distance is further? Well, I hope you're saying neither one. They're the same. That's exactly what we want you to notice. They're the same. It's the same distance if we're going from our house to work or work back to our house, if we're saying taking the same roads. That's what we want you to notice. And that is an important part of the commutative property. So let's see what that looks like in terms of actual manipulations and then in terms of numbers. So hold on and we'll be right back. All right, welcome back. Well, if you've seen any of my recent videos, you know that we went out on a walk and I collected a bunch of rocks because I love collecting rocks. Some of the kinds I like to collect are like interesting crystals or things, but I also really like super smooth, flat rocks that are either oval shaped or round or nearly round. So as we were walking along, we collected a lot of rocks. So we're going to use these rocks to help us understand the commutative property. So let's start with the commutative property of addition. So what if I started out with 4 rocks, and I'm going to start out with 4 big ones, so it's kind of easy to see. So we've got 4 big rocks, and then to that, I'm going to add 6 little rocks. 2, 3, 4, 5, 6. Okay, so I've got 4 big rocks and 6 little rocks. If I put those together, how many rocks is that? Well, hopefully you're saying, well, that's an easy one. I even know a fact that can solve that. And I hope you do. That's great. But for right now, pretend you don't know the fact. Pretend you're just thinking about starting with 4, and then to those 4, you add in 6 little ones. Start with 4 big and add 6 little. And you say, oh, okay, that gives me 10 rocks. You're exactly right. But here's the essence of the commutative property. What if we instead started with 6 little rocks? There's our 6 little rocks. And to that, we added 4 big rocks. Well, how many is that? It's still 10. Now, you may be thinking, well, gosh, I do that all the time. I always know that if 4 plus 6, I always know I could just do 6 plus 4. So if I'm at a problem and I want to count on, sometimes I'll start with the 6 because I only have to count on 4. Or I could do it the other way if I know my 4 facts really well. Hopefully you're saying, yeah, I use that all the time, but maybe you didn't know it was called the commutative property. How does this make sense with knowing about the morning and evening commute? Because if we start with 6, and we add in 4, we still get 10, just like we start at home and go to our job. But what if we started at our job? We start with 4, and then we add in 6. Just like going the other way when we're driving from our home to work or riding a bus, whatever it may be, the amount of miles we travel is the same. In this case, the amount of rocks that we have is the same. You see how that works? Let's try another example. Now, as much as I would like to act this question out for you, you probably don't want me to count out 4 rocks and then add 97 more rocks. Probably not. We probably want to find another way to solve this problem. Now, 4 plus 97, there are lots of ways you could do it. One way that sometimes people find is easy for them is if they count on. But if I start at 4 and count on 97, that would be like a nightmare. That would be like, okay, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, but still going. No, nobody wants to do that. That's a nightmare. But the commutative property says that we can flip those 2 numbers that are supposed to be added together. We can flip those around. 97 plus 4. Well, I bet you're pretty fast at counting on 97 plus 4. 97, 98, 99, 100, 101. Now, you may have known it another way, and that's absolutely fine. But if you use the commutative property to flip those numbers around, it can really make a difference in the strategies that you have available to you. Because counting on isn't really a strategy that's available to you. It just would take way too long. But it works really well here. Or even the counting up to making groups of 10. If I start at 97 and I count up 3 to 100, and then I just have 1 more left, 101. That's the beauty of the commutative property, is it opens up lots of opportunities for you so you can have different plays, different kinds of plays. And if you've had me before, you know that I say this all the time. Sports teams don't only have one play. If they did, the first time the play might work. Second time, the team would be like, didn't they just play that last play? Okay, well, weird. They're trying to trick us, I guess. By the third play of doing the same play over and over, the team would be like, and we're going to now be done with you because they would just shut them down. They would know what to expect, and there would be no more scoring, and that team would lose every game. Think about, too, if they only had one play that was an offensive play and they didn't have any defense. Or what if they only had one defensive play and no offensive plays? Well, that wouldn't work. The same thing is true for math. You need to have more than one play. If you say, I know one way to solve this, you're stuck. And any time that operation or that strategy needs to be implemented, you only have one thing you can do, and it doesn't work really well for everything. But if you have a variety of ways that you know to solve problems, you're in good shape because then you can choose which strategy to use. Just like teams see how their opponent is working or how they're playing together, they know what the conditions are, where their strengths are, and they choose plays specifically. You can do that for math too. Let's try the commutative property of multiplication. Okay, let's try this one. So this is working on the commutative property, for multiplication. I got to write that. There we go, for multiplication. So we've got 5 times 3. What does times mean? Hopefully you're saying groups of. 5 times 3 means 5 groups of 3. So how many groups do we need, and how many is in each one? 5 groups of 3. So we need 5 groups, and in each of those groups, there's 3 things. So I've got some plates. Let's make that with our rocks. Okay, so here are our 5 plates, 5 groups, and each one needs to have 3 rocks. Now, please grab something and do this along with me. Don't just sit and watch me play with math. You should be playing with math too. Doesn't matter what it can be. It can be rocks. You see me work with Pringles or fruit snacks. What are they called? Smarties was requested one time. So find something that you have a number of and model this out with me. So get 5 groups, just like I've got, and put 3 of something in each one. Okay, I hope you did. Here's my 5 groups, and in each of those is 3 rocks. So how are you going to figure out the answer? Well, if you were just starting with multiplication, you might actually count them up. You might do 1, 2, 3, count on, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. If you were just getting started, you could do that. Now, you might say, well, wait a minute, I know a fact. I know 5 groups of 3. I already know a fact. I know that's 15. You could know a fact. So you could count on, you could know a fact. Maybe you know that multiplication is repeated addition. So you could do 3 plus 3 plus 3 plus 3 plus 3. So you could either count by 3s or add 3 each time. 3, 6, 9, 12, 15. Those are all good ways to do it. But one thing we want to talk about today is the commutative property. What about 3 times 5? You might know a fact and say, well, 3 times 5 is 15. It's the same thing. These two are the same. They're not the same. The answer is the same. The number you get when you solve this problem is the same. But it's not the same problem. The commutative property, we use it sometimes so often that we forget that we're using the property rather than just thinking it's the same. This is 5 groups of 3. What is this? This is 3 groups of 5. So let's pause, and I'm going to put our answer 15 here. Let's pause and model out 3 groups of 5. You do it along with me, and I'll see you in a minute. All right, we're back. I hope you modeled it out as well. 3 groups of 5. So that means I need 3 groups. So in this case, last time I had 5 plates out. This time I only have 3 out. And in the groups is 5. Last time I had 3 in the group. This time I've got 5 in each group. So it's 3 groups of 5. Now again, there's lots of ways you can solve it. Knowing a fact, you already got it. Maybe you want to count up. Maybe you're really awesome at counting at 5s. I know I am. 5, 10, 15. There's the answer. Maybe you want to count on. There's lots of strategies that you can use, but The strategy we're thinking about today is the idea that you can flip those numbers around to be able to open up a lot of other strategies that might work better when the situation is different, when the numbers are different. This is pretty easy. 5, 10, 15. We can get the answer pretty easily. Let's see how the commutative property can help us when it's not a fact that we already know, but something that we can specifically choose the commutative property to help understand the problem and help us solve it. So we'll see in just a second. Okay, we're going to try figuring out the commutative property of multiplication and how it can help us by thinking about area. So you may know the area of a rectangle. To find that area, we can take length times width. You may have called it that before, length times width. Or as we get a little older, oftentimes we switch that to base times height. So you may use base times height. Either one, length times width or base times height. What if we said this is our problem? Here's our rectangle. The base is 14. The height is 5. So what if we said, what if we said we had 5 groups of 14? 5 groups of 14. Now, I don't know my 14 facts, so I'm not really sure what 5 groups of 14 is. There are lots of ways I could solve it, including grabbing a calculator, but if I don't know what 5 times 14 is, I might be able to flip it around using the commutative property and figure out really quickly if I flipped it around to be 14 groups of 5, because I'm great with 5s and a lot of people are. So 14 groups of 5, I might be able to skip count super fast and get the answer. 5 groups of 14, less so. So 5 groups of 14. There's a 14, there's 14, there's 14, there's 14, and there's 14. They're my 5 groups of 14. But what if I turned it sideways and had 14 groups of 5? 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70. See how fast I got that? That's one of the ways it can help us. Because sometimes if we commute them, means flip them around, sometimes it opens up other opportunities or it can connect to something that we know. And that's really, really helpful. So in this case, I'm going to switch it around. I'm going to use the commutative property and I'm going to switch it around and say, what's 14 groups of 5? And I found that answer pretty quickly by counting by 5s. Okay, but you say, what if I'm not working with whole numbers? Does it still work if I'm using decimals or fractions? Remember, decimals and fractions both kind of show the same thing. They show a part of the whole thing. So you can write 1/2 as 1/2. You can also write it as 5/10, 5 out of 10 pieces. You could write as a fraction as 5 out of 10 pieces. Those are all different ways to write the same, but they all mean the same thing. They all mean you're talking about half of the whole of something. So let's try the commutative property using fractions to see if it works, if the commutative property works when we use fractions. So you may not have fraction strips at home. You might not have fraction pieces at home. So this might be a time that you follow along, but you might want to make some fraction strips too. And a quick Google search will help you find some and help you make them if you don't know how to. And then you can even follow along with your own materials. All right, so here's the problem I have. 1/2 plus 3/4. Now, you've heard me say it 100 times, and it always makes more sense for math if you connect it to something that you know, so that it's not just numbers, but it's numbers that mean something. That's really important to help you remember and understand math. So let's connect this 1/2 and 3/4 to something we know. Well, let's pretend that we were having a party and we ordered 2 pizzas. After everybody ate all the pizza they want, there was 1/2 of one of the pizzas left, and there was 3/4 of the other pizza left. We want to know, can we put those two together into one box to save it for another time, put it in the fridge? Or is it going to be more than a whole thing, less than a whole thing? How much pizza do we have left? So let's figure it out. So we're going to use this. There's a half. If you're not familiar with these are just blocks that stick together to make the whole thing. So there's our half a pizza. And there you can see our 3/4, 3 out of 4 pieces. So here's our half. We put it together with our 3/4. Now, I know a fact, a half and 3/4. I do a lot of cooking, and so I know that if I need to put a half and 3/4 together, I know my answer is going to be 1 1/4. I just know that because I've done it for so long. You might not, and that's okay. So, look at this. When I put a half and 3/4 together, it gives my answer 1 whole and 1/4, which tells me probably wouldn't fit just in a regular box, the regular pizza box. I might have to put it in a Ziploc bag or maybe save both boxes or something. The question then is, if 1/2 plus 3/4 gives me 1 1/4, what if instead I had 3/4 of the first pizza and half of the second pizza? How much would I have then? Well, by now in the video, I hope you're knowing it's the same thing. We can flip them around. 3/4 plus 1/2 is going to give us the same answer. It's not the same amount, like as in having a half a pizza, having 3/4 of a pizza. That's not the same. Having 3/4 of a pizza of this kind and a half of that kind, that's not the same. But when we put them together, the amount that they make is the same. So if I took 3/4 of the first pizza and added it with a half of the second pizza, the answer is still the same. Let's see if this works with fractions. Let's see if the commutative property of multiplication also works. All right, we know that the commutative property of addition works for whole numbers. We know the commutative property of multiplication works for whole numbers. We just proved that the commutative property of addition works for fractions. Let's see if the commutative property of multiplication works for fractions. Can we use fractions in the same way? So I have the same numbers, but this time I've got 1/2 of a group of 3/4. Now, multiplication of fractions, remember, is quite different than addition. 1/2 of a group of 3/4. And remember, I'm using this circle dot to mean times, to mean the multiplication sign. As we get older and start working with more variables, more letters in math, we usually switch to this dot in the center so we don't get confused whether that x means multiplication or whether it is a variable x. So 1/2 times 3/4. 1/2 of a group of 3/4. So what are we going to start our drawing with? 1/2 of a group of 3/4. We're going to start out with the 3/4. Again, let's give this a context. Let's say I baked some brownies and there are 3/4 of the pan of brownies left. Please do this along with me. You can make up a different problem even and stay a step ahead of me and see if you agree with me, but please do some drawing here. It's really important our brains learn math differently when we draw or make some kind of artistic representation. So please do this along with me. Draw your brownies and cut them into 3/4. Okay, here is my pan of brownies, and there are 3/4 of the pan. Now you might say, well, Miss Cooper, that doesn't work in my family. As soon as the brownies come out of the oven, there's 0. So I can't ever do this because my sister always eats all the brownies, or my brother or dad, grandma, whoever it may be. Now, it's probably true. I totally hear you because that would happen in our house too. So, but here we go. We've got a pan of brownies. Someone ate 1 of the 4ths, and we have 3 of the 4ths left. But now along comes your sister, and she's going to eat half of what's left. She's eating half a group of 3/4. So what would that look like? Well, let me get a different color here. That would look like her coming along and taking out half of what's left in the pan. So she's going to take this whole piece as well as half of that piece. She's going to take and eat that section. She just ate half of what was left of the 3/4. So half a group of 3/4. So the question is then, how much of the brownies did she eat? If you're going to tell on her, especially, like if you're going to go and say, hey, my sister's eating all the brownies, I'm trying to do math with them. I don't know, maybe that could work. Give it a try. So how are we going to figure this out? Well, this is easy. We can say she ate 1/4, but she also ate this half of 1/4. How are we going to talk about the answer of how much she ate? We're going to have to recut them just like she did. We're going to have to recut these pieces. Let's do that. Okay, I hope you can see that. I've taken each of those 3/4 and even the empty space and cut it into half just like she did. Now, we can see that she ate one of those pieces, two of those pieces, three. So she ate 3 pieces, so we know the answer is 3. And what size are the pieces now? 1, 2, 3, 4, 5, 6, 7, 8. There's 8 pieces now. So she ate 3/8 of the pan of brownies. Now, that hopefully is familiar from a few lessons that you've had about multiplying with fractions. What about, though, using the commutative property? 3/4 of a group of a half. You might say, wait a minute, I'm only starting with a half, a group of a half. How could that possibly work? Well, let's see if it does. This is 3/4 of a group of a half. So that means another day you bake brownies again. But they come out of the oven, you're going to let them cool. You come into the kitchen and there is a half a pan of brownies left. This time it's your brother and he's eaten half. Let's draw that. Okay, so you've got half a pan of brownies left. And you come in and you're so disappointed. You say, ugh, I keep making these brownies. My family keeps coming and eating them. I'm trying to do math with them. So you've got half a pan of brownies left. So you think, okay, I'm good. Got half a pan of brownies left. My meeting with the teacher is coming up. I'm going to be in good shape. But this problem says that your brother comes back a second time. Now, this time he's going to eat 3/4 of a group of a half. 3/4 of a group of a half. Here's your group of a half. He's going to eat 3/4 of it. So that means we take this half, this group of a half, and we have to divide it into 4 pieces because he's going to take 3 out of those 4 pieces. 3/4 of a group of a half. So here he comes with his knife for the brownies, cuts it into 4 pieces. And how many is he going to eat out of that? He's going to eat 3 of them. He's going to eat 3/4 of a group of a half. So he eats that one, and he eats that one, and he eats that one. Now, how much is this? Well, we know it's 3. He ate 3 pieces there. Out of what size pieces are those? Well, you might be able to say, if this half of the brownie pan is cut into 4, I know that in theory, if this hadn't been eaten before, that half of the brownie pan would also be cut into 4. So the brownies would be cut into 1, 2, 3, 4, 5, 6, 7, 8 pieces. So he ate 3 of those 8 pieces. Look at this. Those pictures look very different, don't they? Just kind of like when we had the plates with rocks. One time we had 5 plates with 3 rocks on each. One time we had 3 plates with 5 rocks on each. That looked different. This looks different. The reason it looks so different is because it means different things. In this case, we still have some brownies left over, don't we? In this case, we have one measly little 1/8 brownie left. The pictures look different, but the answers are the same. The answer is 3/8 here, 3/8 here. That's the commutative property. It means even though the problems are different, they look different. When two fractions are being multiplied, if you want to, you can flip them around, coming right back to the commute, the morning and evening commute. It's the same if you go to work from your house or if you come back to your house from work. When we're multiplying fractions, we can flip them around and we still get the same answer. I hope this has been really helpful for you to understand the commutative property. I hope you look for our videos on the associative property and the distributive property. See you next time.